Good afternoon. My name is Wellington. I'm a graduate student of Statistics at the USP, Universidade de São Paulo, e UFSCar, Universidade Federal de São Carlos. My supervisor is Professor Cibele M. Russo, and together we are working about the public security and crime data in Brazil. So in this presentation, we'll show the theme about the geospatial modeling of crime in São Paulo state. The presentation will divide in several parts. The first part is the motivation, the reason why we do this work. The second part is what we're talking about our models, that is SAR modeling. The third part is applying SAR model to our state data. The final part is the discussion, and we will leave some reference. Okay, let me do a brief introduction. Our model, spatial autoregressive modeling, is important because he takes into account the geolocation of the data as well as their underlying spatial dependence. So, in this work, we will use SAR model to describe crimes in cities of São Paulo states, which is in Brazil, and including also the monthly seasonality present in the data. Okay, now we will talk about the security problem. As we know, Brazil faces a giant, the Brazilian society faces a giant and considerable challenge about the public security. And that's why we decide to work together about this theme. And we work about this theme using the statistical methods and computational methods. So when we are considering the data of the techniques of data visualization, and after that data pre-processing, it is possible to observe the geography of São Paulo state and the state locations that are more likely to have crime. So here in this choroplast figure, that is a choroplast plot of the São Paulo state crime per capita, that we use the total number of crime in the period between 20 and 20 and 21 is represent of each city with a correspondent color in this map. So this figure shows that the metropolitan and coast area as a place with higher values of crime per capita, pointing that the crime are more likely to occur in the developed and touristic city. So here we come, if we see this figure here, we can see that this is state of São Paulo in Brazil, and here is the capital of the state São Paulo, that is the city of São Paulo. And we can see clearly that the city of São Paulo has higher crime per capita than the cities nearby. This is also applied to the coast areas. They are more likely, those two places are more likely to occur crime than other regions. Okay, when we're talking about the data for analysis, we have collected data from various sources. The crime data we were obtained from Secretaria de Segurança Pública. It is available in this reference here. The demographic data were obtained from SEAD, that is the Sistema Estadual de Análise de Dados. The geolocation information was obtained from IBGE, Instituto Brasileiro de Geografia e Estatística. And to fit the SAR model present in this manuscript, we have chosen the data from 2011 to 2012, as they do not have missing data. So, as shown in the figure below here, the correlogram, which shows a correlogram between different variables of crime. So it is possible to observe the strong correlation between different types of robbery. So here in this choroplast plot, we have there are several variables available, such as, for example, homicide, injuries, rape, and robbery. And if we based on this color here, that we this color here, we can see that the different type of drawberry, they have a strong correlation. Okay, let's now go to the SAR modeling. The SAR model, spatial autoregressive model, also known in the literature as spatial lag model or mixed regressive model. He is an extension of the linear regression model, and he is given his equation below here. So this part is a traditional linear regression, and this new part here is what defines the specific characteristic of the SAR model, that is rho, the matrix W, and the second Y. So we call the rho the spatial regression parameter. W is n by n neighborhood matrix that accounts for the spatial relationship among the spatial data. Epsilon is the error term that is independent and identically distributed. Y is a dependent variable, X is an independent variable, and beta is a coefficient of X. So when we are talking about how can we generate the matrix W, we generate that matrix W by using the spatial dependency, and the spatial dependency can be defined as a relationship among the spatially adjacent pixel in a neighborhood with a spatial framework that is a regular grid space. So we took a photo and we analyzed their relationship by pixel. So when we use this following expression to explain how the matrix W in the SAR model is formed. So in a simple 4-neighborhood case, the neighborhood of ij pixel of the regular grid are shown in this equation here. So for the neighbor ij, we have 4 neighbors: north, east, south, and west. And if we see here, this phi, the phi is a row dimension of spatial framework, and Q is a column dimension of a spatial framework. So the ij pixel of the surface will fit the phi times I minus 1 plus j row of the non-row standardized neighborhood matrix, which is called C. So the authors, they state that based on this formula here and this formula here, these two formulas, the author states the following matrix of C matrix, which we say that the elements of the matrix C at those position of the row, they will have value of 1, and the other element will be 0. So the row standardized neighborhood matrix W is formed by first finding each row sum, and we will have n quantity of row sum, since n is equal to phi times q, and then we divide each element in a row by its corresponding row sum. So in other words, the matrix W equals to D with a -1 potential times C, where the elements of the diagonal matrix D are defined as their diagonal with this diagonal value with this value, and the others are 0. So here we have an example of the matrix C and D. Here is a non-normalized neighborhood matrix C, which is only 0 or 1. And this is a normalized version, which is W. And we can see we have half, we have 1/3 or 1/4. So since the pixel may have 2 neighbors or 3 neighbors or maybe 4 neighbors, we can have different value of this element. So that's why we have half, third, 1/3, or 1/4. Okay, now let's talk about the derivation of the ML function. As we can see that the ordinary least square are not appropriate to solve the model described in equation 1. So we need to rewrite the equation 1 to the following equation here. So this part here is generated by took this part to the other side of the equation and take y as the evidence. So that's why we have here I minus rho times w. And this t here begins to 1 until n. It's the index for n successive observation. So let's assume that the disturbance or error t is distributed normally, independently, and identically with the mean of the error term equals 0 and variance of sigma squared. So the set of n such equation here, we can be compiled as the equation 1. Okay, let us assume the disturbance t, which are the elements of the vector epsilon and are distributed independently distributed independently and identically according to a normal distribution defined in equation 4. So, and we also call the I minus rho times W as matrix A. So we have here the error term as distributed normally as shown in the equation 4. And if the vector has a multivariate normal distribution, just like in our case, so we will have this equation here that we congregate every observation together to form a multinormal distribution, which we define as a big sigma as sigma squared times I. So here we have the multinormal distribution. Then after congregating every value of the observation and generate a multivariable multinormal distribution, we can use this formula to generate the log likelihood of the distribution, which is shown in this expression here. And we suppose that this part equals matrix A, so the formula could be expressed like this. And if we consider the beta hat and sigma square hat, and then we replace beta hat with beta and sigma squared hat with sigma squared in the equation 10, here we can have finally we have the log likelihood function to be optimized for rho, which is this part. And then we will take this part of the equation and we will use to derivate based on rho. So that's the final part of our work. That is we will use derivative-based optimization using Newton-Raphson algorithm. And to use this algorithm, we will need to compute the first derivative log likelihood function, as we said earlier. And this will give we will use the rho parameter to derive this part of the equation, which will generate this result here. Okay, now we talk about the application. Inspired by the work of Bezerra, we used the total crime of each city in São Paulo state in 2011 and 2012 with linear regression and SAR model. We took account of the seasonality of total crime number within a year with a series with lag of 20 months we were used as independent variable and the current total crime as a dependent variable. So we can show the fit results in the table here. So in this table here, we can see the variable which are constant, total crime, after with lag of 12 months, and the matrix W. We have here the coefficient and the standard error and the Z statistic. Also, we have the log likelihood, the archaic information criteria, the Schwartz information criteria, which were all here. And finally, we were talking about our future work. We will use more sophisticated model to obtain a spatial temporal model. We will analyze the data based on time and the location. And after doing this, our main goal is to predicting crimes in different cities when we take into account of the location and the time. Okay, in the final, we will see that these are the main references that we used to develop our work. And thank you for watching my presentation.